All right, so today we're going to begin our first step into the world of electronics. And your first step in learning how to not only work problems, but also learn how to design and create these types of circuits. So the starting point for modern electronics, we have to look at some semiconductor physics. Now I want to warn everybody, in case you're worried, this is not a semiconductor physics course. I am not going to go into the details of how these equations are derived. There are people here at Vanderbilt University who can teach this material far better than I can. And there are great courses you can take in device physics and semiconductor physics if you want to. I'm going to give you guys kind of a bird's eye view. We're going to learn enough about how these devices work to give you kind of a mental picture. And then at that point, I'm going to go and start writing the equations, and we'll start working these problems. So that's going to be our goal for this class. Okay? So let's first consider the p-n junction. What is the p-n junction? That is the basis for everything we're going to be learning about in the class this semester. And typically we use silicon to create p-n junction devices. Now, other materials can be used to create these types of junctions and these types of devices. Germanium, for example, was among the very earliest. Whenever people first started making the earliest transistors, they were germanium. But silicon is common today. We've learned a great deal how to use it. And silicon is a very preferable manufacturing material because it is quite literally as cheap as dirt. All right? Silicon makes up a big chunk of the Earth's crust, right? So it's very easy to work with silicon. It's a plentiful material to work with. So how does a p-n junction work? Well, first we want to kind of go and look at the atomic level. I'm going to draw a lattice of silicon atoms. Now, when we take silicon, we actually can form crystals out of silicon. And so this represents the silicon atoms in a crystalline array. Now, actual array would be three-dimensional. So I'm just drawing a two-dimensional slice of it. But if you remember back to your chemistry classes, you know that we have covalent bonds that can be formed with outer electrons in the outer shell. And as it turns out, a silicon atom has 4 electrons in the valence shell. All right, so I'm going to go ahead and I'm going to kind of draw these in. And once again, I'm kind of doing this two-dimensionally. So silicon atoms have 4 electrons in their valence shell, but the valence shell of silicon can actually have 8 electrons. There's room for 8. And so what silicon does is it forms covalent bonds with the adjacent silicon atoms. So that, in effect, every silicon atom has 8 electrons by sharing 4 electrons with their neighbors. So we've got a crystalline array, 4 covalent bonds. In effect, every silicon atom gets to have 8 electrons. So you've seen this concept before. I'm sure you saw this in high school chemistry. You've seen it in your chemistry courses here at Vanderbilt University. So this is a well understood concept. Now, every once in a while, one of the electrons in one of these covalent bonds will gain enough energy to essentially break free and pop out of its covalent bond. And when that happens, that electron becomes a free electron. So in this case, for example, let's say that one of these silicon atoms loses an electron. So what will happen is an electron will pop loose. Use a different color for this. And we normally represent that electron with the letter N in semiconductor physics. But this electron will be a negatively charged particle. It pops loose from one of the silicon atoms. So now the silicon atom has an imbalanced charge. Normally, the number of protons and electrons equal each other in an atom, okay? But in this case, this pops loose, which means that this silicon atom now winds up with a net positive charge. Now, the total charge is still the same. It's just that we've now separated those charges because we've had an electron break loose. So here's our free electron. And we have a silicon atom that now is missing an electron with a net positive charge. There is, what we say is, we call this a hole. There's a hole in the valence band now where that electron has been lost for that silicon atom. So a hole is left behind with a net positive charge. Okay, now the interesting thing about semiconductor physics is we actually treat holes as if they were actually like charged particles, physical particles, almost as if they were the counterpart of an electron. I mean, obviously that's not really what they are. There are places where electrons have broken loose from atoms. But from the viewpoint of the equations in semiconductor physics, we treat holes and electrons as basically both the same thing, a way of allowing electricity to travel. They're basically carriers of electricity. Okay. Now, you'll have this happening all over the lattice. You'll have electrons gaining a photon through thermal energy. They'll gain enough energy, they'll break loose, and then you'll have some free electrons always kind of like wandering through the lattice. And then from time to time, a free electron will then be captured by a silicon atom and then will recombine again. So the net charge in the entire crystalline array never changes. Net charge, positive plus negative, is always equal to 0. But what you have is you'll have current carriers due to those free electrons. And what this means is this crystalline lattice, because of those free electrons, has now the ability to let charge flow through it. It has the ability to conduct electricity. So silicon, in its pure form, due to these free electrons, is a conductor, but it is really a very resistive conductor. So it's a conductor, but it's not a very good conductor. We have a name for that. We say it's a semiconductor. So when you have something that acts like a very poor conductor, but it does conduct some. It's not an insulator. It's not a conductor. It's not like metal. Metal's a really good conductor because there are huge numbers of free electrons in metal. But in silicon, there will be some, not a whole lot, and so it'll be a semiconductor. All right, so given this behavior, what can we do to try to modify this behavior? To create what we call a p-n junction. And I should point out that N refers to the free electron, and normally we'll use the letter P to refer to the hole. So that's where Pn comes from, just from our designations for holes and electrons, the positive and the negative charge carriers. So to create a p-n junction, what we're going to do is we're going to do a technique called doping. We're going to deliberately introduce impurity atoms into that semiconductor lattice, into that silicon lattice. So we can put in two types of impurities. An impurity that provides us with excess electrons, we say, is an N-type impurity. And an impurity that provides us with excess holes, we say that is a P-type impurity. So depending upon the type of impurity atoms we use, we can either create excess holes or excess electrons. So how do we make that work? Well, let's consider phosphorus. Phosphorus has 5 electrons in its valence shell. Remember, silicon had 4. So what we're going to do is we're going to introduce a phosphorus atom in that array of silicon atoms. It's going to replace one of those silicon atoms. And phosphorus will very happily form the same form of covalent bonds with the adjacent silicon atoms. But the problem is phosphorus has an extra electron it doesn't need to form those 4 covalent bonds. It has 5 electrons in its valence shell. So in this case, phosphorus is quite willing to give up that excess electron and doesn't want it back. Once it has 8 electrons in the outer valence shell, it's happy. Of course, I'm kind of anthropomorphizing atoms here, but I think you guys understand what I mean by this. It's more than happy to release that extra electron. So in this case, what we find is that phosphorus atom will give up that free electron and doesn't really want it back because it now has its 8 electrons in its outer valence shell. So that 5th electron is kind of a spare. Okay? So it easily gives up this free electron. And once that free electron is in the lattice, it's not really going to be recombined or used again. It's going to basically drift around because none of the other phosphorus atoms really want it back. And so every phosphorus atom that you introduce into that lattice is going to give up a free electron that's going to tend to wander around that lattice. So we say that phosphorus is an N-type donor. It donates a free electron to the crystalline lattice. Silicon that is doped with phosphorus becomes an N-type semiconductor. We call it doping. We're adding impurities. So we say we're doping the silicon with those impurities. So questions about this? Hopefully pretty straightforward concept. So here I can generate lots of free electrons by adding phosphorus atoms, mixing them into that lattice. Yes?
I have a question about that free electron. Since all the silicon are trying to reach those 8 valence electrons, isn't it possible that that free electron kind of disrupts all the bonding? Like, wouldn't the silicon just say, oh, well, I'll just take 3 bonds and I'll just take that extra free electron since no one wants it?
Well, the silicon is always going to be forming the 4 extra bonds with the other atoms around it. So all the silicon in the lattice is always going to be forming and want to form and keep 4 covalent bonds. So any extra free electrons drifting around, yes, there will be an occasional silicon atom that will give up an electron and then recapture it just from thermal energy like we talked about before. But these electrons that are given up by phosphorus generate, in effect, excess carriers that nobody wants. All right, so that's what's happening here is these phosphorus atoms are releasing these electrons. Some of the free electrons will be captured by other silicon atoms or even occasionally by another phosphorus atom. But for the most part, most of these free electrons will just wander around through the lattice. They're not easily captured or recombined. All right. Now, incidentally, I also want to point out that when the phosphorus atom gives up that electron, it now has a net positive charge, right? But in this case, this is not a net charge that wants to capture an electron. Once again, that phosphorus doesn't want another electron back. But the net charge, positive plus negative, is still equal to 0. So this act of these free electrons breaking away doesn't change the fact that, electrically speaking, the entire lattice still remains electrically neutral. So that's phosphorus. There's another type of impurity we can add. And incidentally, phosphorus is not the only N-type donor, but it is certainly one of the most common N-type donors. But other materials can be used to create donors as well. Yes?
Are all the creators, are all the atoms that are used in this way all have 5 valence?
Well, yes, all the phosphorus will all have 5 electrons in the outer valence shell.
Other non-phosphorus options to do the same thing?
There are other types of N-type donors you can have that may have 1 or more. Okay, once again, it depends on the type of impurity. So I think there are other types of impurities that have been used in the past that could give up more than 1 electron. But phosphorus is by far the most common. I don't think that in terms of manufacturing you see any large deviation in modern semiconductor physics from phosphorus and the other one, boron, I'm about to talk about. But once again, I'm not the physics expert. I'm sure that somebody here who wanted to talk about device physics could give you a lot more information about different types of impurity options for semiconductors. Again, I'm just showing you guys the basic concept because I want you to understand that. But by all means, I do advise you, if you want to learn more about the actual physics of these devices, we have some excellent instructors here who teach good courses in this material if you want to learn more about this at the physics level. But that's not what this course is about. Okay, so next, let's talk about boron, another impurity. Boron, we call this a p-type acceptor. It has 3 electrons in its outer valence shell. So in this case, if we were to put boron in a semiconductor lattice, boron will very quickly form covalent bonds with 3 silicon atoms. But the 4th silicon atom, it cannot form a covalent bond because it does not have an electron to share with the other silicon atom. So in this case, what we have here is a place where that boron would love to have an electron to complete those 4 covalent bonds. So what will happen is a free electron comes drifting along, and if one shows up, that boron atom will grab that to complete its outer valence shell. So in this case, it accepts a free electron to complete that 4th covalent bond. Now the question is, where did that free electron come from? Well, the only place that free electron could have come from was from a silicon atom somewhere else in the lattice. There aren't any phosphorus atoms there. It's only boron. So either do phosphorus or boron, either donor or acceptor. So in this case, it gets that from some other silicon atom that must have given that free electron up. Which means that by capturing that electron, a hole is left in the crystalline lattice. There's a hole left in some other silicon atom somewhere in that lattice. So in this case, we have lots of holes. Yes?
I was just wondering, is there a reason you're saying like P-type acceptor and like N-type donor?
Because the N-type, it's donating a free electron. P. Well, are you saying to say, do you use the words P-type and N-type? Are they redundant? Okay, well, yeah, in a sense they are. I mean, if I say something's N-type, obviously it is donating free electrons. But I'm just using the terminology now to clarify it to everybody. Later on, we're just going to say N and P, right? But right now, like I said, I want everybody to have that mental image. All right, so if I put boron into this semiconductor lattice, what I have here is a P-type semiconductor. So, for N-type, we have excess electrons. For P-type, we have excess holes. And both excess electrons and excess holes will be charge carriers. Now, as I said, a hole is not really a physical, it's not actually a particle. There's no such thing as a, it's basically not the equivalent of an electron with a positive charge. But in terms of how we visualize holes versus electrons, when you look at the textbooks and look at the equations, it is more convenient to create a mental picture where we think of holes as being the positively charged counterparts of electrons. Even though really what a hole actually is, it's a place where a silicon atom has given up its free electron. But we kind of operate and treat it as if it were actually a charged particle by itself. And that's exactly how textbooks do it, and that's how I'm going to do it as well. But just keep in mind, the idea of an excess hole is basically, it's kind of a mental convenience that we use to kind of think about how to write the equations. Okay? Now, if I add either lots of phosphorus or I add lots of boron to a silicon lattice, I'm going to create more charge carriers. And so in this case, what I find is doped silicon is a better conductor of electricity than pure silicon. In fact, a great deal of the effort that goes into semiconductor manufacturing is to precisely control those impurity levels, to get yourself just the right amount of doping level to make sure that you get the kind of properties you want out of the silicon. Okay? Questions about this? hopefully pretty basic. And like I said, this is kind of based on chemistry stuff you guys have seen before. Now, before we want to move on, I want to add one more definition. In an N-type semiconductor, there are lots of free electrons drifting around, and we say that electrons are majority carriers. The majority of current carriers are electrons. But that doesn't mean there aren't any holes. You're still going to have silicon atoms that are giving up their electrons from time to time. And so even though the overwhelming majority of current carriers are electrons, you will still see a few holes, even in an N-type semiconductor material. And we therefore say that the holes are minority carriers. Now for a P-type semiconductor, as you might guess, that's reversed. Holes are the majority carrier. Electrons are the minority carrier. And we'll be seeing this definition of majority versus minority later on, especially when we start talking about bipolar junction transistors. Okay? Questions? All right, so we've figured out how to create excess charge carriers in pure silicon. Now we're going to do something interesting. I'm going to take a section of N-type silicon and a section of P-type silicon, and I'm going to move them together. I'm going to make them form a junction with each other. Yes?
If you try to send a charge through a P-type semiconductor, what if the electrons that you're trying to send through just go into the holes instead?
Well, they're always going to be, okay, keep in mind, the entire thing is still electrically neutral. Okay, so the positive and negative charges still cancel out. So as electric current moves through, okay, keep in mind electric current is going to be the movement of charge carriers. And assuming that any flow out of the semiconductor, they're going to be replaced by others flowing in. But you're always going to have that certain level of excess holes just because, once again, the phosphorus atoms, for example, don't want them back. And so you're always going to have that level in there. This is really all kind of balanced out by the thermal energy going on. So you're always going to have these electrons popping loose and staying loose because of thermal energy. Yeah?
What's the typical ratio between the dope, the phosphorus or boron and the silicon?
Oh, I couldn't tell you off the top of my head, but usually it's on the order of, 1 atom per million or 100,000. Not a huge number, okay? Because for one thing, the phosphorus and boron atoms are not the same size. They don't really fit well in the silicon lattice, and they'll actually cause a dislocation in the lattice. So you can't put too many in. But you want enough in there to give you basically a level of current conduction that you can control. But once again, I'm the wrong person to ask that. There are faculty here who could just rattle numbers off the top of their head, but I'm not that person. But yeah, but it's not great. It's not huge. Okay, so given this, let us now create a p-n junction. Let's take an N-type and a P-type material and let's push them together. p-n junction is formed like so. I have a p-type and an n-type semiconductor. And I'm going to form a junction between the two of them. And so over here in the n-type semiconductor, we have lots of free electrons drifting around in that n-type semiconductor. In the p-type semiconductor, we have lots of excess holes available in that p-type semiconductor. And once again, we're going to kind of operate under the fiction that those holes are just like electrons in the sense that they're mobile particles drifting around in the lattice. And we're going to make those two touch. Okay, now here I have on this side a high concentration of electrons. Over here I have a high concentration of holes. And I'm going to make those two semiconductor materials touch each other and form a junction. Now, what physical process now takes over when you have a high concentration of something here and a low concentration there? What physical process do we call that? The movement of material from here from high to low concentration. Diffusion. It's diffusion, yes, exactly. We've learned about diffusion. Diffusion is going to take place. Holes are going to diffuse this way. Probably the electrons are going to diffuse this way. Holes are going to diffuse that way. So from high to low areas of concentration. So what's going to happen is this. There's going to be a region where holes and electrons are going to cross. And so let's use this. So electrons are going to cross over from the right to the left, and holes are going to cross over from the left to the right. Now, think what happens here. As these holes drift across into this n-type region, those holes are going to combine with the electrons that are in this region here, and they're going to cancel each other out. So one interesting thing happens is this. The holes drift across, they combine with the electrons in the n-type region, and they're going to create a region of positive charge. But in doing so, when the holes come across and they combine with those free electrons, they deplete this area of any free carriers. So the holes capture the free electrons, and then basically I wind up with positive charge accumulating, but no free carriers. Same thing happens with the electrons drifting across. They combine with the excess holes. And in this case, you wind up with a region that becomes positively charged. Negatively charged, I'm sorry, because of the electrons coming across. But in this case, once again, combining with the holes eliminates the free carriers. And so the holes combine with and remove the free carriers in the n-type region. The electrons combine with and remove the holes in the p-type region. So near this border where they go across each other, they will create a region that has a net, or I should say a net potential across it, voltage potential across it, but it is depleted of any free carriers. So this creates something which, not surprisingly, we call the depletion region. Okay? Now, this depletion region has an interesting property. As this depletion region forms, we start having net positive and net negative charge. And so what we have is it starts to create something called a potential barrier. And what happens is this. As this potential barrier forms, you start to accumulate positive charge in this side. The positive charge starts repelling the holes away, any additional holes that try to come across. It pushes them away because of that positive charge. The negative charge starts to accumulate on this side. It starts to repel any more free electrons. So as that potential barrier is formed, it halts any additional diffusion, any further diffusion. And you can actually plot this. If you actually go through, you'll see books will actually plot the voltage, okay, the electric field created across this potential barrier. And then as you move across that barrier, you effectively have this voltage, this potential barrier that blocks any further diffusion of free carriers across that region. Now once again, I am hand-waving in the extreme. There is a great deal more to all of this than what I'm doing here. I'm just trying to once again give you guys a mental image. If some professors here who are specialists in semiconductor physics were to see this lecture right now, they'd be aghast. They'd be horrified because I'm teaching it in such a simplistic fashion, but that's fine. I want it to be simplistic because I want you guys only to have that mental picture. So, don't hold me to any physical accuracy to this. Once again, I'm trying to just give you guys kind of a picture. All right. Now that we've done this, probably the lower axis is the distance going across. So in other words, this lower axis, okay, the middle here is that center axis. So this is the distance, okay, from this. So in this case, 0 is the actual point where they merge, and if I go to the left and to the right, then the potential barrier starts to form as I enter that depletion region and then maximizes as I exit on the other side. Once again, I'm waving my arms, arm waving. Okay, so now that we've got this picture, this depletion region forming because of the diffusion of those free carriers, here's the next part. Let's take this, and I'm going to take that structure, and I'm going to, now notice here, I have two terminals coming out of each of those two regions, the p-type and the n-type region. And this is just like 2112, right? Circuits 1. I've got an element with two terminals. So what am I going to do? I'm going to connect a voltage to those two terminals. I'm going to create what's called a reverse biased connection by doing the following. Take a voltage VR. And notice the polarity because that's critical. Here's my p-type and my n-type regions. So I'm connecting the negative side to the p, the positive side to the n. Keeping in mind, once again, we have lots of holes, and we have lots of electrons in those two regions. So what's going to happen here? All right, now I've got lots of holes here, and I'm connecting this to the negative part of the power supply. So this negative terminal of this voltage source is going to attract holes. So we're going to say to ourselves, we can think about it this way. Holes are going to flow out of this p-type region and be attracted towards that negative terminal on that voltage source. Now, not really, of course. Holes are not actual physical particles, but we're going to pretend that they are. The excess electrons we have, they're going to be attracted to the positive terminal. Electrons are going to flow out of the n-type region. Now, as that happens, as I lose carriers on both sides, as they flow out, what happens is, as the net positive charge decreases in the p-type region, the depletion region is going to grow. It's going to get bigger. And as electrons flow out of this region, the positively charged p depletion region on this side gets bigger. The depletion region grows. So it gets bigger. And so the depletion region grows as we start losing these free carriers on both sides. And as that happens, the potential barrier gets bigger, gets stronger. And as it grows, it is going to oppose any current, any free carriers crossing that depletion region. And so we find in reverse bias, essentially no current can flow through that diode when it's reverse biased. When the positive end of the voltage source is connected to the n-type region and the negative end is connected to the p-type region, because that makes the potential barrier get bigger, which makes it even harder for carriers to diffuse across that region. Now, there is a very tiny current that can flow because there are minority carriers. There are minority electrons in the p region. There are minority holes in the n region. So you actually do find a very, very tiny current. I'm talking about typically picoamps or femtoamps will flow due to those minority carriers. So we will get a very, very tiny current flow, but usually small enough where in most applications we can ignore it because it's so tiny. But it is there. It can be measured due to minority carriers. Now, I can really, ultimately, I can force the issue. If I make the voltage of this voltage source high enough, I can create a potential across this PN device to the point where literally it will punch through that depletion region. If I make a high enough voltage, I can literally force current to flow through there, just if nothing else by just ionizing atoms because the electric field gets so strong. And that technique is called breakdown. We'll talk about that later on. So you can actually force the current to flow in reverse bias if you make the voltage high enough. But for now, we're not going to worry about that. But we'll come back to it later. Now let's take this and let's flip it around. And I'm going to take the same thing, except now I'm going to flip the polarity of that voltage source. This is a forward biased connection. And in this case, the positive end is connected to the P region. The negative end of the voltage source is connected to the N region. Now we're kind of flipping this around. Now what we're going to see is holes are going to flow out of the positive end. Once again, we're treating the holes like charge carriers. Holes are going to flow out of the positive end of the voltage source and flow into the P-type region. Over here, I'm going to have electrons flowing into the N-type region. Now, as this happens, I have more and more holes and more free electrons accumulating here. And as that starts to happen, what's going to happen is the depletion region starts getting squeezed by these carrier concentrations, is a way to think about it. And so now the depletion region shrinks due to these increasing concentrations of carriers. Furthermore, I've got excess holes and electrons in both these regions, which means now diffusion will keep taking place. These excess concentrations now want to travel across, and the depletion region is being squeezed, and now it's easier for them to start traveling across. So therefore, holes and electrons now start diffusing across that depletion region again. So as we start squeezing this depletion region and shrinking it, the potential barrier is also going to decrease. And now we're going to see more diffusion of carriers across that junction. Now, as these electrons travel across, they're going to be canceled out by the holes that the voltage source is supplying. And as the holes travel across, they're canceled out by the electrons that the voltage source is supplying. So this becomes a continuous process. We're going to have free carriers diffusing across. They're going to be canceling out the free holes and the free electrons, which are immediately then replenished by the voltage source. And this process will continue. So, as this happens, let's think about this. Think back to circuits 1. What is the defined direction of positive current flow according to circuits 1? Direction of holes or direction of electrons? Direction of holes, exactly. It's against the flow of electrons. So what this means is I'm going to define a current I, which is going to flow through this device. And as I increase VF, the current increases as well. What you'll find is you need to take VF and make it large enough to overcome the initial potential barrier that's in that silicon. And typically that means you have to increase VF to about 0.6 to 0.7 volts in silicon, and then you're going to start to see significant current start to flow across that depletion region. So somewhere within the range of about 0.6 volts to 0.7 volts, you're going to see a very large current start to flow through that device. And this increase in current is exponential in nature. Once the current starts to flow, just a tiny increase in voltage causes a much, much larger current to flow. It is literally exponential, to the point where you can literally have tens or hundreds of amperes flowing through a diode like this very quickly, or probably through a p-n junction like this. And obviously, if you keep doing that, you'll literally burn the device out with too much current. Yeah?
Does it follow Ohm's law?
It does not follow Ohm's law. We're going to see later on. It does not. This is, in fact, a non-linear device, okay, as we're going to see. So, we see that in forward bias, we can have milliamps, amps, tens of amps, hundreds of amps if we wanted to. In reverse bias, it's going to be small, picoamps, femtoamps, nanoamps, very, very small currents versus very large. And it only takes about a forward voltage of about 0.6 to 0.7 volts to start that current flow, just enough to overcome the initial potential barrier. And incidentally, different materials, different semiconductors will have different potential barrier values. So silicon classically has about 0.6 to 0.7. So what does this act like? In reverse bias, current is essentially zero, except for minority carriers. Very, very tiny. In forward bias, we can have huge amounts of current flow. So this acts like a diode. And we used that word last time. What is a diode? A diode is a two-terminal device that only allows current to flow in one direction. Now, as I said last time, the idea of a diode happened a long time ago, happened in the late 19th century. Edison saw that it happened. He wrote about it, the Edison effect. It was a curiosity. That's interesting. Current only goes one way through it. Edison really didn't grasp what he had, didn't know how to use it. But by the time radio had come around 20 or 30 years later, people were beginning to realize that there were some really useful applications of an element that could do this. They could only allow current to go in one direction. Okay, so that is your arm-waving picture of how a diode works. So from this point on, we're now going to jump right into how do we represent a diode on a schematic, and how do we use it, and what are the equations that governs its behavior. So let's move right into that. Like I told you guys, strictly arm waving. All I want is the mental picture. But now we're going to move into what this class is all about, and that is the actual circuit elements and how to use them. So just as in 2112, we had different schematic symbols for capacitors, inductors, voltage sources, current sources. Same thing here. This is a schematic symbol for a diode. We call one terminal the anode and one terminal the cathode. The anode is the p-type region of the diode. The cathode is the n-type region. So we have this little triangle and then that straight line. Incidentally, anode and cathode, those are weird words, aren't they? Anode and cathodes are leftovers from vacuum tube technology. So in the early days of vacuum tube diodes, we called those terminals anode and cathode, and the name is still with us today with semiconductor devices. Okay, so once again, just as I told you guys in 2112, you can orient this any way you want to. But what's important is current flow across it, or current flow through it, I should say, and the voltage across it. So we're going to have a positive voltage, VD, from the anode to the cathode in order to have current flow. And we will have a current, ID, flowing from the anode to the cathode. So this is what we're going to represent our voltage and our current for. Now before we jump into physical actual diodes and start writing equations and drawing circuits, I first want to spend a little bit of time, and the book goes through this as well, first kind of building up the idea of what it means to have an element that only allows current to flow in one direction. So before I actually start writing the equations for what a p-n diode behaves like, we're first going to spend a little bit of time talking about the ideal case. So I want to first talk about the ideal diode. And for the ideal diode, we're going to make some simplifying assumptions about the behavior of this element. So I'm going to do a little graph where I'm going to plot ID versus VD. And for the ideal diode, what I want to do is I want to create the simplest case that shows this direct current flow in one direction. So I'm going to draw it like so. If the voltage across the diode, VD, is negative, then this diode is going to be in reverse bias. and the current will therefore be equal to 0 for any amount of reverse bias. So I'm going to assume ideally there's no minority carriers, there's nothing. Current is 0. Another way I'm going to say is this. I'm going to say this diode is off. It's in reverse bias, nothing flows through it. It's like an open circuit. Now over here, it's going to be a little different. Forward bias, I'm going to assume that the voltage is positive. But in this case, I'm going to assume for the ideal voltage that VF only has to be epsilon above 0. It's an infinitesimally small positive value, effectively just 0. And when we have this infinitesimally small positive voltage across the diode, we say it's in forward bias, and then any amount of current you want will flow through that diode, or it's on. Yeah?
Why is it VF not VD?
I'm sorry, VD. I'm sorry. Thank you. That should be VD, not VF. Thank you. I was thinking VF as in forward biased. My apologies. Okay. So VD. Thank you. Okay. So we're going to first look at diodes from this ideal case, because it's easy for us to visualize how it works. And here's kind of the way to think about it. When the diode's off, it's like an open circuit. When the diode is on, it's like a short circuit or a wire. And that's going to help us visualize the behavior of a diode. Either it's off, it's open, it's on, it's a wire, it's a short. Okay? All right, so we note for the ideal case, VD will essentially we're going to treat it as if VD is equal to 0 when the diode is on. So there's no voltage drop across it, okay? So in effect, if it's a wire, and we thought about it as being a resistor, so a resistor has a wire, so the resistance is equal to 0, then if we think of it as a wire, VD is equal to 0. So in the ideal case, we're just going to say it's 0. So I'm talking about this epsilon plus, but really we're just going to say it's either 0 or it's negative. That's the only two cases we can have. All right? Let's draw a couple of circuits that are going to give you an idea of what you're going to expect when you start looking at actual electronic schematics. Okay, does this look familiar to you guys? The way I'm drawing those power supply terminals? That should be familiar. We did this when we talked about op amps. We drew this. It is implied that there is a 10-volt source in this circuit that I'm not bothering to draw. So just as a reminder to everybody, there's an underlying assumption here that I've got a 10-volt source connected from ground to that terminal. But in order to make this schematic neater, I'm not going to bother to draw it. So I'm just going to draw this plus 10 volt terminal, but you know that voltage source is there. So this kind of shorthand is incredibly common. It's going to be used right off in the book, and you need to start getting used to it. All right, you're not always going to see every element drawn. They're only going to be implied. Now in this case, let's think about this. I've got two diodes, and the diode can only have one of two states. It can either be on or it can be off. And in this case, I've got voltages in these circuits. So let me ask a question. Is that diode on or is that diode off? It's on or off?
On.
You say it's off. Okay. You say it's off. OFF. Okay, I just want to make sure what you're saying. Okay, the math makes it hard. My apologies. Okay, you're saying this is off. Okay, let's test that assumption. The diode is off. No, watch what I'm doing here, guys. You're saying the diode is off. If the diode is off, the current through that diode must be equal to 0. Which means the current through this resistor is equal to 0. What's the voltage drop across that resistor if the current's equal to 0? 0 volts, right? No current through the resistor. What is the voltage at that node? 10 volts. Okay, I have 10 volts on the anode and 0 volts on the cathode. Is that diode reverse biased or is it forward biased? It's forward biased. It's forward biased by 10 volts. Does that make sense for the ideal diode model? No, this is contradictory. Your guess is wrong. Don't feel bad. We'll all be guessing. You're all going to, I guess. You guess and then you check your assumption, which is exactly what we did here. You guess wrong, but you check your assumption. It can't be off. It makes no sense. Therefore, it must be on. And if it is on, the voltage across that diode must be 0 volts. And therefore, the voltage at this node is 0 volts. What is the current flowing through that resistor? 10 divided by 1K, 10 milliamps. Therefore, 10 milliamps by KCL is also flowing through that diode. Does that make sense? Yeah, okay. It's forward biased, okay? What do you think this one is? It's off, okay. Using the same logic, okay, I flip it around. If it's off, okay, then that current must be equal to 0, which means this current's equal to 0, which means I've got 10 volts here. I've got 0 volts on the anode, 10 volts on the cathode. VD is minus 10 volts. Is that reverse biased? Absolutely. That diode is off. Okay, guys, you're going to be doing this for the rest of the semester. You'll see a circuit. Rarely can you just look at a circuit and tell what the operating condition of the device is. You make an intelligent guess or assumption, if you want to call it that, but then you check and see if it makes sense. All right? So we'll look at some more examples and more diode circuits next time, and we'll look at more and see how to practice and learn this technique. Okay, guys, see you on Thursday.